Okay, so simulation at 43%, and I notice we reaching close to a half cycle. So I just like to show the voltage. So this is 18 volts, and we have in here 14 volts, right? So you're gonna get perfect 1-to-1 ratio, right? So this is really good so far, right? So 14.74, well, 24. You notice I have some high steps. I have like 2 microseconds steps are set for. It will do pre-adjustment. You can see it here, and yeah, so it just only 2 cycle doing, right? And we can see what the voltage settle down to be. Okay, so this finish here. Let me take a long hard stare at this result. Hide this guy, hide this guy. Pull up the model builder and settings. Right, so you can narrow these guys down, close these guys. Okay, so we just want to look at the results. I will go to voltage. As I said, do 2 cycle, and that was it. Right, so 1 and 2. So we have a, this is the voltage input is plus minus 18 volts, and the coupling we have like 14.682, right? And yeah, call 14.5 or something like that, right? Let us look at, we have a resistor for load, which is we have a resistor for load, right? And I basically did not, wow, I don't think I supposed to have this resistor divide down by, I wonder if I have it. I will know now. Supposed to be down to our load. Okay, this need to go down to be less than that. This have to be n p, right? So this supposed to go down to point with 200 micro ohm, 200 milliohms, right? Sorry. So this supposed to be 200 milliohms. When I was running simulation, I forgot this secondary. I load all in parallel. So since I load all in parallel, I need to actually give it a parallel load. If it was like 0.99 something ohms or like 1 ohm, so would that be series? This is not the case, right? So I load this thing 5 times less. So 5 times less we load, so you know it would be 8,000 divided by 83 or about 87 or something like that. Right, so let's say 8300 divided by 5, about 1600, oh, 1600 watts. So we're going to look at this resistor is R1, right? So we look at resistor R1. Right, secondary load in resistor. and we'll give it a global prefix. You go to the circuit, case 1, and we will go to R1 and we'll look at the dissipated power on that. So dissipated power on that is 220 watts, so that is 14 volts, right? So this will be really 14, let's say 14.5 volts, right, divided by 0.9987 something something, whatever, right? So we have that. um, we parallel. I'm not sure how it represent across all, but I will determine that afterwards. So if I say 220 divided by 5, 44 watts. So I will look into that, right? And I had to do the proper loading on this. So that was that. Okay, so that the voltage, look at the flux density, right? Right, so we have the flux density here, and we can see we have an even distribution. Go to here, same thing here. Now you're going to notice something over here, right? The flux density on top, right? About that and about that, right? So both of them, let's get this in alignment here. Right, you can notice one fading out and this one appearing, right? Now the reason for that is that the primary foil is generating a magnetic flux that inducing itself onto the core, and the core will take that around and induce it in the secondary. So we send in a current to excite the current flow on the primary coil, and we will get a magnetic field that will excite the core, and the core will excite the secondary side, right? And we have a current flow due to the fact we loaded with resistors. So the center now, the current density in the center is something that we will take a look at, and let us look at, I'm going to remove the top core, remove the, oh my bad, right, so what's selected where? I'm going to clear all and clear all, right? So the top region I will just put that is unusual. Okay, this is what's going on here. I need to clear this box out of the way. Select domain, and right. Right, let's come back here now. Right, so that was the issue there, and I will put secondary, in fact I need to put all those guys. This one I will disable this for now, right? and let us go back to animation. Right, as you can see, the density in the core being excited. This is the primary, right? So this is how it should be, not the garbage I had before. Many mistakes are made, and right, so this is perfect, right? And it actually works. Before it wasn't getting voltage because of those issues with the geometry, and so that's that. We have the millitesla. The highest we have is 160 something. I will try to stop it to the highest. Right, so let us go back here and skim through. Right, so come back here. Right, so the highest is about here. Right, so this region over here, we could just pretty much move this across the chart, and you can see the 160 around here. If we click here, we should see let's clear this here. Right, I'll click a region. Right, so the value in this area here is 4.8 out here is 1 point something. Right, oh, my bad, this is the core and this is the foil, right? 4.8 millitesla, which is fine. So this core have 4.8 millitesla. The foil, sorry, the core is this region they're measuring, and there was again a peak somewhere. I was looking for that, right? So the peak is 1 something here. We could come over here, see 160, so we're close to the alignment here. So this is the core, this is the foil, right? The foil is alright in that sense. We're going to have some issues with heating, so we know we need to get that heat out because this could cause failure in that sense, but we don't have that amount of energy saying that we're going to cause that much failure. I will do calculations for these guys itself and I write in the software version to it. Now what is really unique about when I'm doing calculation is this. This is the unique thing about doing calculation, is that with the calculations, everything that I'm doing, we have all these equations going on. Here is about the entire geometry structure, and the frequency, the current, the voltage, the impedance, all these different things, right? So over here now we looking at, okay, we put quantity of 5 MOSFETs. If I put quantity of 1 MOSFET, right? Let us look at something here, right? So we will just draw MOSFETs, right? Right. So we have one batch of MOSFET here. I would say 2, 3, 4, 2, 3, 4, right? 4. So this is MOSFETs over here. A batch of MOSFETs, a batch of MOSFET here, here batch of MOSFETs, batch of MOSFETs here. And these MOSFETs is basically, we have them like a bridge here, and these guys right underneath here. So this will be like 0 volts, which is the ground really, right? And this one here will be the battery, which will be your 18 volts, right here, 18 volts, and your transformer coil will be over here, right? So this is a H bridge, right? Zero voltage transient. So that is ZVT, they will call it zero, my bad, zero voltage transient. Some might have a ZST, ZVS, things like that. So we have zero voltage transient itself. When this switch in, it will have a resistance here, and when this one closes, it'll have a resistance here, right? So we have a resistance of all these guys that will have a voltage across it, and also a resistance there at a current flow. So each MOSFET will have a current flow, have a total current flow, a total resistance, while the voltage remain the same across all, right? If we have group 1 here and we have group 2, right? Group 1 and group 2, right? We have one MOSFET here for group 1. We are seeing one MOSFET over here represent like all, like we say we remove all 3 MOSFET and have one MOSFET. That MOSFET will have a power rating of 321 watts. It will have a on resistance of 1.4082 milliohms, or either ohms here, and the current that flowing through the entire circuit here will be 477.5 amps. Now if we pretty much put 2, right, MOSFET, we get 160 watts. So for this argument's sake, put 4 MOSFET here, and since we running 4 MOSFETs, right, the MOSFET dissipation heat per MOSFET will be 80 watts per MOSFET. The current handling of each one of the MOSFET will be handling 119 amps. The lowest, well, the highest ohmage that you could go to is 5.6326 ohms, right, milliohms, right? So each one of them will have that. So this is the configuration of the MOSFET that you need to match, right, per MOSFET, right? And so you'll be able to drive the transformer. If I put a 5, right, I have 95 amps at 7 milliohms. Now when we're trying to match this, we have a gate region, which will be, we have a MOSFET, and this MOSFET here now, right, this MOSFET will have a capacitor value here, and this area here will have a capacitor value over here, and across this region here will have capacitor value here, right? So we have a gate capacitance, and once we apply a voltage coming up to the gate capacitance here, right, once you apply a voltage and this has to conduct this capacitance here, right, this one here will come straight across here. This capacitor will double with the capacitor here. So just to take into account, right, we have our power losses discharging this capacitor, which is when we close it, we discharge the capacitor, so heat release, and this from the drain will bring it down to the source. So this capacitance from here to here, this will come and join over here, and we end up with this capacitor across here doubling. So the capacitor that double in here, it will have a heavier current that's going to divide over here. So we have all effects that happening that will have an issue. So that's a whole different story there. So when we choosing the MOSFET, we look at, you know, if we could get probably somebody who have a less gate capacitance, that means we will have a less carrying current. And if we have a less carrying current, impedance will be a certain. This is something that, you know, it will be varying according to. So if you could get a less gate capacitance, and you will have to look for the one with the most less gate capacitance measured in nanocoulombs, and the lowest you could get, try to match it and see. So even if you have to set up more MOSFETs and to match the gate capacitance, it'd be good for your driving circuit. Meaning now when you have a this region here, this is your rise time and fall time. This is where all your heat is start to occur in your MOSFET. So you don't want that, so you try to match that. Now if you use some powerful MOSFETs, you could think that, hey, you're pretty much handling things good. Well, to a point, right? You will end up with a longer slope, right? Because the gate junction to carry much current, you will end up with a larger slope. So the rise time and fall time will be very lengthy in time, and you will end up with issues where we will consider those issues to be something like this, right? So when we have a power surge, we have a power surge like this and a power surge like that, right? So let us say the transistor itself have 0.6 volt, because we have 0.6 volts across each transistor. So the transistor, the region over here is 0.6 volts at 95 amps, 95.5 amps, right? So we have this voltage across here. This multiplied by this equal the wattage that we see in here, which is the 64 watts, right? Now when we're looking at this, now we're looking at a situation where we will have 60 something watts in this region here, 64 watts, right? 64 watts. And this lengthy amount of power over here, let us call that probably 1000 watts, right? So this is 1000 watts rise time and fall time. So due to duty cycle and frequency and time, there's a math you could work that out, right? I didn't bother to do that. That is part of the simple engineering, right? So that power will be showing up. It's not happening in this region. It is happening in this region here, the rise time. So you want to have your rise time sloping much as possible, sloping down, right? So we do have to deal with that region of energy. We will get a very narrow pulse here, which is minor, and this pulse will be very minor. When we do the math, we will recognize that we have a lower power rating, so we need to distribute that. That is something like a sine wave, which we have root mean square. That's a useful energy here, right? We could use these areas here. Technically something similar to, right? So we try to get no problems with the MOSFET itself, right? So that's that.